Hi, it's time for another math easy solution to discuss further into conic sections, and this time look at conic sections in terms of polar coordinates or polar equations. And this will be going over a more unified theorem for conics as opposed to the different theorems that I went over, or different definitions for the parabola, ellipse, and the hyperbola in my earlier videos. So now we'll look at a more unified theorem that's easier to write in terms of a simple polar equation. So let's just jump right in. It's going to be a pretty interesting video. So conic sections in polar coordinates. So first off, recall that parabolas, ellipses, and hyperbolas are called conic sections because they result from intersecting a cone with a plane as shown below. So ellipse, if you have a two-sided cone like this, an ellipse is cutting through both ends of, or just cleanly through one of them, and a hyperbola is cutting through one side of just one, and then it goes through at the bottom over there. So that's hyperbola, gets it like this. And then there's the ellipses, and is a circle. Yeah, a circle is an ellipse, is a flat one, would be a circle. And then a hyperbola is cutting vertically across where it goes through both of these. And then you get two shapes like that on the hyperbola. So very interesting stuff. So now also recall from my earlier videos that that we defined the parabola in terms of a focus and a directrix, and I'll go recap on that soon as well. But instead defined the ellipse and hyperbola in terms of two foci, so it wasn't using a unified theorem. And here is the parabola theorem. So the parabola is the distance. The theorem involves the distance to the foci and to a straight line called the directrix are equal. So that's when we have a parabola. And here is how it looks like. So here is the parabola shape like this, just a set of all points, and then there's a vertex right at this point. And if we draw a straight line and then the focus is over here, then the distance to this point on the parabola, the distance to the directrix over here, is equal to the distance to the foci over there, and the center axis is called the axis over there. And then so at any point here, so if you go over here, it's also equal. If you go over here, this is going to be the same distance across here. And that's how the parabola is defined, using a focus, the f, and a directrix like that. And now recall the ellipse is the sum of the distances to the foci are constant. So for an ellipse is a set of all points where, again, the sum of it is of the distances to the foci are constant. So for example, if you have a point across here, then a distance from here to here and here to here, then when you add these up, they equal the same as a distance from here to here all the way to here to here. So anywhere you go, the sum is going to be the exact same. So you could even visually see it if it points over at this point, then the distance from the foci, from this foci 1 to over here, and then when you add up to this one, it should equal the same from here to here. Because notice how it's smaller here, but now it extends further out, as opposed to this one here is more even up. And then so then the distance right like that, p f1, and this is p f2 to the second foci are constant like that. Just erase all this. And now the hyperbola. Yeah, recall that the hyperbola was defined as the difference of the distances to the two foci are constant. So similar to this one, instead of the addition, we're looking at the subtraction. So this is when we have the set of all points all the way across here. And then basically if you have a point here, the difference in these distances, so pf1 minus pf2 is equal to constant over there, or plus or minus constant, depending on if you subtract this from that, etc. So if you go somewhere around here, then the difference between this and this, the difference between it's going to be constant as well. So as opposed to adding for an ellipse, we minus for a hyperbola, and then the parabola just uses a directrix or a straight line and a focus like that. So just different, yeah, much different than the other two. So now, but in this video I will explain, or I explain a more unified treatment of all three types of conic sections, and this time in terms of just a focus and directrix. So instead of using the two foci or any of this, we'll just stick to a focus and a directrix. So that's all we're going to be sticking to. It's going to be very interesting. So furthermore, if we place the focus at the origin, then a conic section has a simple polar equation which provides a convenient description of the motion of planets, satellites, comets, and so on. So very interesting stuff. We'll look into it. So here is the theorem, or unified theorem, and I'll be proving this in later videos, but I'll go over it here right now. In a summary video right now. So let F be a fixed point called the focus, and L be a fixed line called the directrix in a plane. So on the same XY axis graph, on the same graph. Let E be a fixed number called the eccentricity, and the set of all points P in the plane such that the distance P to F, so from the directrix, from the point to the focus divided by the distance from the point to the line, or the directrix, so L is the directrix, and then the ratio is equal to E, the eccentricity. That is the ratio of the distance from from F to the distance from L is the constant E. So the ratio from the point to F and then from the point to L, like that, is going to be constant E. And this is defined as being a conic section, and the conic is, and then if E is less than 1, so the ratio is less than 1, in other words, this is larger than this, so the distance to the line is larger than the distance to the focus, we have less than 1, that's an ellipse. And if it equals to 1, the ratio, if it's exact same, then it's a parabola. And you can actually see the parabola one, it's pretty straightforward. Distance equal the same. So there's foci, distance to it, there's directrix, equal distance, ratio is going to be the same. And that was a quick proof for that one. But I'll prove it in more concrete terms later. Anyways, so that's parabola is 1 equals 1, and the hyperbola is 1 E is greater than 1. In other words, the distance to the focus is larger than the distance to the directrix. And now MES, note the eccentricity is always positive since it is just a ratio of the distances, and they're all just absolute value distances, so it's always going to be positive. You're not going to get a negative one. And also I will prove this theorem in a later video, so stay tuned, or later video, or videos depending on how many I do. Might do them all separately, but anyways, so stay tuned for that. And the theorem here is illustrated below, and this looks similar to the parabola. So what we have is, let's just write this like this: x and y. There's the x, there's the y axis, like that. There's the origin. So what I'll do now, let's say we have a curve, or just a conic that looks something like this, like that. And now what I'll do now is I'll draw a, let's say the focus is going to be somewhere. So it's going to look something like this. Focus is going to be over here. Here, I just fix that up. So this is the focus like this, and I'll call it F, like that. And then what we'll have is, let's say we have a fixed line. It's going to look something like this. And this is our line L, which is our directrix. So it's called L, it's the directrix. And then this is the set of all the points on the conic, and it's going to be, I'll draw a point, let's say we have a point here, P. So the point here, P, has a distance from here to here is going to be just the absolute value of P. Write it like that, so distance, absolute value of it. And then what we have is from here to this line is going to be the perpendicular line. So the closest distance to this line is going to be perpendicular like that. This is going to be our PL, because that line is L. So distance PL, like that. And then basically the eccentricity is going to be the ratio of the distance to the focus. So E equals to PF over the distance to the line. So PL, like that. And this is basically the theorem, like that. And I'll prove in later videos that it is in fact, whenever E is different, it's going to be either parabola, ellipse, or hyperbola, depending on if it's less than 1, greater than 1, or equal to 1. And now the main motivation for this theorem is that it can write a conic, all three conics, in simple terms when written in polar coordinates or polar equation. So here's a theorem in terms of a simple polar equation. So a polar equation of the form r equals to e, and I'll write e d like this, and then we have r plus or minus e cos theta, or you could write this if it's a vertical one, r equals to e d r plus or minus e sine theta. So if it's any form like this, then this basically represents, I'll write this, I'll just draw a line here. So this represents a conic section with eccentricity e and the focus at the origin. Yeah, so when we place it at the origin, it becomes like that. So we can do the angles and polar equations. And then the conic is an ellipse, again, if e is less than 1, a parabola if e equals to 1, and a hyperbola if e is greater than 1. So we could write a simple equation like that in polar coordinates. And here's the following figures illustrate the different polar equations for various conics. And again, I'll be going over these in more details, well, especially the proof of the theorem. So if you have r equals to ed1 plus e cosine theta, and the this is when the directrix is on the right side, and then we get this equation. And again, the focus is always on the center. If the directrix is on the left side, x equals negative d. Conic's going to look something like that. And then again, f is always there. This is for a minus. If it's a plus e sine theta, it's going to be a vertical one going downwards like that. And then if it is a this one's negative y equals negative d directrix, it's going to go upwards like that, and then we have negative e sine theta like that. And also interesting, as I'll show later videos, if you have a ellipse or a hyperbola, it will have you could have two foci, but the thing is the definition just uses the 1, so you'll always have that 1, even though we'll have 2, it'd still be collected in it. For example, a hyperbola will have an extra foci over here, but nonetheless this still all encompasses the conic. So very interesting stuff once I get through it in later videos. So a note, let's put a MES note. I will also expand on the different variations of the polar equations for conics in a separate video, so stay tuned. So this video is more of a summary because it's a lot of info in there. Last but not least, recall the connection between polar coordinates and Cartesian or rectangular coordinates. Just to quickly recap, if you haven't already watched my earlier videos on polar coordinates. So here's to connect the two. If you have x and y like this, and this is the positive x-axis is the polar axis like that. And then if you have a point here, P, so this point has in polar coordinates would be the distance to the origin like this. So write this origin like that. The distance is going to be r, or the ray in polar coordinates, r, and then the angle is theta from the polar axis. And in Cartesian or rectangular, this is, well, I'll just draw a line like this. This is our y, and this is our x distance or coordinate like that. And this is going to be r theta, and also it's going to be the point P, X, Y. So the same coordinates, just different ones like that. And if you look at cosine, and now if you look at the definition of cosine, adjacent over a hypotenuse, this equals to x over r like that. So then in other words, you can move the r to this side, you get x is equal to r cosine theta like that. And likewise for sine theta is equal to opposite over hypotenuse, so y over r. And then move this r over there, we get y coordinate equals to r sine theta like that. And also note that we could just use Pythagoras over here, so that we have also r squared equals to x squared plus y squared, and that's just using Pythagoras. As well as if we use tan theta number is just sine theta over cosine theta. The r's will cancel, and basically what we'll end up having is a y over x. And in fact, this is actually by definition as well of a tan function. So I'll just write this one here is by Pythagorean theorem, or by Pythagoras. So Pythagorean theorem. And then this is actually by definition. This is a more general definition of a tan function as opposed to using opposite over adjacent. Even for cosine, I'll explain that further. This is by definition. So this is just relating the rectangular with the polar. And also want to make a note, these equations are valid for all angles and in fact are the general definitions of sine and cosine. So these ones here are in fact general definitions like that, and they'll work for any angle, even this one here for tan. So they're all definitions. For example, if we had an obtuse angle, so an obtuse angle like this between pi over 2 and pi, or in other words 90 degrees and 180 degrees, or if you believe in tau instead of pi, you can go from tau over 4 to tau over 2. Anyways, that's a discussion for a later day. The relation between Cartesian and polar coordinates remains the same. And so for example, if we had a different angle like this, so this is just the x, y, and that's the polar axis, and let's say we had a point here, and then this over here is going to be our r. This is our angle like that, so it's obtuse between pi over 2 and pi radians, or 90 degrees to 180 like this. This is nonetheless, if we have it down here, this is still going to be x, and this is still going to be y. That's our new, this is our new p equals to, let's write this as p r theta equals to the coordinates p x y. Yeah, in this case, nonetheless, even over here, we have cosine theta is equal to, it's going to be equal to, by definition, so x over r. And y, yeah, I mean, and then sine as well, equals to y over r. This is actually the more general definition, so it doesn't need to be opposite over hypotenuse, because the angles over here, yeah, you could still think of it as opposite over hypotenuse of the inner angle like that. This is actually by definition like that. And then if you move that around, x is going to be, well, it's going to be r cosine theta. So nonetheless, you'll still have x equals to r cosine theta, and this one's going to be equal to r sine theta. And here, last point, the only difference here is that the cosine function is negative for obtuse angles, and hence the x-coordinate will be negative. So here we'll have r cosine theta, and then this is going to be negative, so we'll have a negative value, and it's going to be on the left side like that. And the y is still going to be positive over there. And you could even recall the graph of a cosine function. It looks something like this, x, y. Yeah, I'll just draw this even further out, like this. So there's the x and y. Recall looks something like this. I'll draw on this side. So it looks something like that and goes all the way back there. This is from 0. This is our cosine theta, like this. And then this is at our pi over 2 radians. This is at pi, and as you can see, here is positive and then it becomes negative between here where the obtuse angle is. So then we'll have a negative value for cosine, negative x value. So yeah, I just get a negative value over there, but for sine, if you graph it out, you'll see that it's positive still. And then past the 180 degrees or pi radians, it becomes negative for y, and it goes to this negative side. Anyways, yeah, so that is all for today. Just one last thing, just hashtag stay tuned for my later videos. Yeah, I'll be going over the proof of the theorem and more detail on the different variations of this simpler formula for polar equations. I mean, in polar equations of the conic sections, and also go over the proof that this is in fact a unified theorem that encompasses all the parabola, ellipse, and hyperbola conic sections. Anyways, that's all for today. Hopefully you enjoyed this quick summary video of what's to come, and also going over the conic sections and polar coordinates. Anyways, that's all for today. Thanks for watching. Like always, you can download these exact notes in a link in the description below, as well as viewing these notes on Steemit. Follow me at MES, and also make sure to check out my my cool math and science forums on Reddit and Vote, as well as my Discord chat room. So check those out. Anyways, all for today. Thanks for watching, and stay tuned for another math easy solution.